Welcome students to your favorite channel Pradeep Sir Classes as PSC, and today we are discussing about the next part of Gauss's law, that is AC Verma solutions, and it is based on the numerical king series. And I discussed today question number 7, 8 and 9, and is more important. So first of all I suggest you that uh, take your copy and pen as well as the AC Verma book, and if you have not that particular book, you can take a PDF from Google Play Store. Okay, so let's start with the next one, that is question number 7. And so question number 7, students, when I always suggest you that when doing that particular numericals, you have to clear your concepts. There is the concept is question number 7 to 9, and all the concepts related with Gauss's theorem. And I repeat again, the Gauss's theorem states that phi, that is net flux. Flux means, students, and the number of electric lines of force are crossing a particular surface perpendicularly. So what are the number of electric lines of force crossing that particular surface? That is called flux. And phi net you have to calculate if this is the definition particular, and you have to calculate that flux, that is phi equal to E dot S, since this is a scalar quantity, scalar function and electric field. And when you use that particular flux, then flux you have to know what is the unit of flux. That is unit of flux equal to Newton by Coulomb, that is electric field E equal to F by Q, E equal to F by Q, and surface area, that is meter square. So Newton meter square by Coulomb is the SI unit of flux. And when you go through a particular surface, then you have used that particular formula. But if you want to calculate the net flux generated through a particular surface, that is closed surface, or it may be hypothetical surface, Gaussian surface, then and it is so simple, that is phi net equal to Q inside by epsilon naught. So that is the main point. If a charge, suppose this pen, we consider this is suppose 2 Coulomb charge, and if we kept within my hands, then it is Q by epsilon naught, that is Q means 2 Coulomb by epsilon naught means 8.85 into 10 to the power of minus 12, and the unit is Coulomb square by Newton meter square. So you have to know that particular value, that is again I repeat, it is 8.85 into 10 to the power of minus 12 Newton meter square, sorry, Coulomb square by Newton meter square, Coulomb square by Newton meter square. So what is epsilon naught? I discussed this is what is epsilon naught in the previous class, and if you know, if you want to know the particular concepts related with epsilon naught, then go to the previous lecture. So phi net, that is the net flux, means if a charge is given and different directions, that is it is a three-dimensional concept. If all the flux, that is electric field lines, are penetrating that particular surface, then what is the number of that particular field lines? That is called flux. So flux, net flux, you have to calculate the net flux. This is equal to Q inside by epsilon naught. If that particular charge is within my pocket and I close that particular pocket, then the flux generated through the pocket is Q by epsilon naught. That is, you have to take that particular charge divided by upon 8.85 into 10 to the power minus 12. And if the charge is outside that particular surface, suppose this is a surface and a charge is kept at that particular point, then the contribution of this flux, that is flux penetrating that particular surface, is equal to the outgoing surface. So the net flux contribution due to that particular surface is 0. That means the total number of flux penetrating that particular surface, the field lines that penetrate that particular surface, is equal to the outgoing flux. So for the question number 7, you have to know that what is the charge enclosed within the surface. So let's write down the numericals and then try to solve it. So question number 9, find the flux of electric field through a spherical surface of radius r due to a charge of 10 to the power minus 7 coulomb at the center. So you have to calculate, find the flux of the electric field. Flux of the electric field. Yes, it is for electric fields. Also you can calculate flux through of a magnetic field. So here you have to calculate, find the flux of the electric field through a spherical surface. Through means that particular Gaussian surface it may be, or a particular surface if it is given. So find the flux of the electric field. Flux of electric field through a spherical surface. Through a spherical surface. Through a spherical surface of radius capital R, due to a charge of 10 to the power minus 7 coulomb, 10 to the minus 7 coulomb at the center, and another equal charge at a point 2 or away from the center. Yes, 2 to the minus 7 at the center, and so due to a charge of this at the center, and another equal charge means this is the value 10 to the power minus 7. Another equal charge kept at a distance 2r, at a distance 2r, yes it is 2r, away from the center, away from the center. So first of all, students, you have to note down that particular question. That is question number 7, and it's from Gauss's law, and the page number is 141. And if you have not that particular book, then you have to download a particular PDF, that is AC Verma Numerical number 7 from Gauss's law. And so this is the question. First of all, as I say, the question you have to write down and then figure out that particular one. So the figure is like that. This is a closed surface and this is the center, and its radius is given. This is r radius, and another charge is kept at 2r, at a 2r distance apart, that is from here. Here another charge of q, and this is q, and the value of q is given 10 to the power of minus 7. Okay, so 10 to the power minus 7. So there is a charge, and first of all, students, you have to think that the contribution of flux from a closed surface is due to the charge enclosed within the surface, and for that particular charge the contribution is 0, because when flux generated from that particular one, then it penetrating the surface, the number of electric lines of force penetrating that particular surface is equal to the outgoing flux. So the contribution of flux due to that particular charge is 0. So for that particular flux, 0. Flux linked, if the question is said that what is the flux going or entering that particular surface, then this is a particular answer is given. But if the what is the net flux, if it is a question is given, then what is the net flux through that particular surface, closed surface, then the answer is 0. Then the question is what is the number of net flux through that particular contribution. So here it is q, and for that particular one a flux is generated like that. So the contribution of flux due to that particular charge, is phi equal to simply q inside by epsilon naught, or 10 to the power minus 7 by epsilon naught, that is 8.85 into 10 to the power minus 12. and this is the answer, and the unit is Newton meter square by Coulomb. So the final answer is this, and you have to calculate 1 by 8.85 as, and then 1 by 8.85, and that will be it is so simple. You have to calculate it. 1.1 into 10 to the power of 4 Newton meter square by 1.1. The answer will be 1.1. So 1 by this 1.1 into 10 to the power of 4 Newton meter square by Coulomb. Okay. So this is question number 7, and question number before the discussing about question number 7, we have to take another interesting example that is that the realization of flux. I think it will be better. So question, there is an example. There's an example. You have to do that particular one because it is more interesting, and it is yes, it is in 130 page. So charge capital Q is distributed uniformly or a ring of radius small r. There is a ring, and there is a ring. Suppose it is not a particular question, it is taken from an example. Yes, a ring Q is distributed uniformly or a ring of radius small r, and a sphere of equal radius r is constructed with its center at the periphery of the ring. Find the flux of the electric field through the surface of the sphere. Oh yes. So the question is, there is a ring of radius. There is a ring of radius. There is a ring of radius r. So this is the radius, and a charge capital Q is uniformly distributed over that particular ring. So it is a ring, and charge is distributed, that is uniformly distributed. Charge is uniformly distributed over the ring, and you have to consider a sphere of equal radius, such that that particular center and that particular center, such that that particular center lies on the two sides of that particular radius. If I think so, this is the center of that particular sphere. This is not ring, it is a sphere, and it is a ring. So ring is, we know that it is 2D concept, and a sphere means it is 3D concept. So if you imagine that a particular suppose a football, there is a sphere and a ring is introduced like that. So it is a football and a ring is introduced, but a small portion. What is that particular portion? If the half of the ring is within that particular football, then the contribution of flux is it is total charge Q, so will be Q by 2. That is, the Q by 2 amount of charge is within that particular sphere. Within that particular sphere, Q by 2. So the flux will be Q by 2 epsilon naught. But is the half of this portion is within the sphere or not? So the question is that no, and this will be a greater amount for that particular one, and you can imagine it by just seeing that particular figure. So what is the logic within this figure? And if we consider a particular point, suppose this is A and this is O dash, and this is A and this is B, and if we join that one and that one and that one, and this is, so this is R and this is also R, because it is the radius of that particular ring and it is also the radius of the sphere. So all the distances are R. So it is an equilateral triangle. So for that particular angle is 60 degree. Okay, so this is 60 degree, this is also 60 degree. That is the particular angle is 120 degree. So 120 degree. So the angle subtended by that particular arc is 120 degree. 120 degree. This is also 120 degree. This is also 120 degree. So the total sphere is 360 degree. So 360 degree, 120 degree is out of 360 degree. Out of 360 degree with the ring, 120 degree, that is that particular portion is within the sphere, that is 1 by 3. So 1/3 of the ring, 1/3 of the ring, that is q by 3 amount of charge. 1/3 of the charge, 1/3 of the ring, 1/3 of the charge, because charge is distributed within that particular sphere, ring. So q by 3 amount of charge is within this sphere. So the contribution of flux, that is this charge, can generate a flux along that particular direction, this amount of charge. So the flux will be phi equal to q by 3 epsilon naught. The question, I repeat again, there is, if you note down, please note down these questions. A ring of radius small r is introduced within a sphere of radius r such that that particular radius can coincides within these two centers, that is O and O dash. And the question is, what is the contribution of flux through this sphere? So the charge, you have to just calculate the charge enclosed within the sphere. What amount of charge is the total charge is given. So that particular portion is within the sphere. That's why q by 3 amount of charge is within the sphere. So the flux is q by epsilon naught. So q by 3 by epsilon naught. This is the answer. So from the two example, that is question number 7 and that particular example, we reached at a particular situation that the contribution of flux, that is Gauss's theorem states that the contribution of flux, the net flux, is equal to q inside by epsilon naught. That is the charge enclosed within a sphere. If we if the pen is within this hand or within a particular, if I take a container and drop down this chalk, and if it contains 2 coulomb of charge or 3 coulomb, any amount of charge, then the flux linked with that particular closed surface, flux linked. If the chalk is given here and it contains 2 coulomb of charge, then the flux generated through or linked through the sphere, through the curved surface as well as the circular surface is 2 coulomb by epsilon naught. So you have to divide epsilon naught with the charge that is enclosed within the surface. So always in Gauss's theorem, you have to think that the particular charge is within the surface or not. If it is not, then the contribution is 0. If it is within the sphere, then the contribution is q by epsilon naught, the net flux. And if you have to calculate electric field, then another method. Then you have to take a definition of electric field, that is E dot S, or integration of a small surface is given, then E dot ds, and closed integration. You have to take a closed integration. If the surface is not closed, it is open. Suppose if you take a glass, and drop down this chalk, and this chalk contains 1 coulomb of charge, then the flux, what is the net flux? Then Gauss's theorem doesn't take any action for that particular, because the surface is not closed. If the surface is closed, then Gauss's theorem tells that it is so easy, that is the net flux is equal to q by epsilon naught. So simple. So the next question is, the next one is question number 8. So write down the question number 8, and this is a numerical king series. So students, you can, all the numericals have done from that particular book as well as from this mind are always a typical example, and it can clear a greater view. So stay with this channel, and I think it will be better. So question number 8 is, a charge capital Q is placed, a charge capital Q is placed at the center, is placed at the center, as the center of an imaginary, of an imaginary this is a hemisphere, imaginary hemisphere, this is imaginary hemisphere, and it's given, you can see that numericals, a charge capital Q is placed at the center of an imaginary hemisphere surface, so full stop, and then using symmetry arguments and the Gauss's law, find the flux of electric field due to this charge through the surface of the hemisphere. So a charge capital Q is placed at the center of an imaginary hemisphere, that is here. Then calculate flux linked with this surface, that is the hemisphere, it is the half sphere, that is hemisphere. So flux linked with the surface, using the point number 1 is, you can use Gauss's law, and the second is symmetry argument. What is symmetry arguments? What is Gauss's law? Already you have know, the flux equal to Q by epsilon naught. I repeat again and again, that is, I want to hammer you that Gauss's theorem is Q inside by epsilon naught, that is the charge enclosed within a surface divided by epsilon naught, upon epsilon naught, and the value of epsilon naught is 8.85 into 10 to the minus 12. So you have to check what amount of charge is enclosed within the surface, but for that particular one there is a hemisphere, and its imaginary hemisphere is given. So it is a hemisphere, but this is not a closed one, and the charge is kept here. So it is open. Suppose you can consider a cauldron, and the charge is given at the center. So the cauldron is opened. So the flux generated along this direction cannot penetrate a particular surface. So the flux generated along that one are the linked flux with the surface. So you have to calculate the linked one. Calculate the flux linked with this surface. Suppose you can think an umbrella like structure, hemisphere, half sphere is called hemisphere. So the flux linked with that particular umbrella you have to calculate. So you can use Gauss's law or symmetry argument. What is symmetry argument? Symmetry argument means, I say for the previous class, that if a charge is given, suppose a charge is given at the center of this room where my camera is at that moment, there is charge enclosed at that particular one, then the flux generated or flux linked with all the surfaces is Q by epsilon naught. It is so simple by using Gauss's law. But if the question is that what is the net flux through a particular surface, then you can count 1, 2, 3, 4, 5, 6. There are 6 walls. There is the flux linked through each wall is 1 by 6 Q by epsilon naught. It is so simple. And this is called symmetry argument. When the charge is at a particular symmetric point, then you can apply symmetry argument. If a bulb is at that particular point, then the luminous flux can lighten all the walls with equally brightened. But if the light is on a particular wall, then somehow some of that walls are equally lightened. So the charge is placed at the center, and then you can easily calculate the flux generated through a particular surface is 1 by 6 q by epsilon naught. But here you can apply the symmetry argument, because if you imagine a Gaussian surface, a closed surface, there is a sphere, then this is the center point and it is at a symmetrical position, that is you can apply symmetry arguments. So what is symmetric arguments? If we calculate the net flux through this closed surface, then it is q by epsilon naught, but half q by epsilon naught, but the half portion is not there, so you can easily write down the flux will be this one, half of q by epsilon naught. So the answer is, this is the answer. It is so simple. So symmetry argument concept, you have to clear your concepts about symmetry argument as well as Gauss's law. And Gauss's law states that the net flux is equal to 1 by epsilon naught times net charge enclosed within that particular surface. So this question is, I think that it will be clear for you. And that is question number 7, question number 8, and question number 9. A spherical volume containing uniformly distributed charge of these, find the electric field at a point inside the volume at a distance of 4.0 centimeter from the sphere. And I think you have to calculate that particular ones. And for the previous class I didn't explain that particular one. There is a spherical or cylindrical one, if it is taken, or like that volume distribution of charge. So I completed that volume distribution of charge for the next day. Suppose it will be tomorrow, and then I do that particular numerical. So okay, thank you. And last of all, I say continue to study. Okay.